Hi students, in this video we are discussing about grating spectrum. Let us see what is a grating spectrum. Before going to that, we have to know about diffraction grating. See what is the diffraction grating. With this grating we have a lab experiment also, like finding the wavelength of a given source, given light source. Let us see what is a diffraction grating. Diffraction grating is nothing but a closed packed, that means closely placed multiple slits. It consists of very large number of narrow slits side by side separated by opaque spaces. See, within inside that grating, how it will be partitioned. See here, E is the width, is a line width, and the D separation distance between two lines. That's I plus D, and the transparent medium that acts as slits, and opaque medium that isn't transparent, it's not transparent, and the ruled lines which indicates E, and it is a transparent material. So the light incident is transmitted through the slits and blocked by opaque spaces. Such a grating is called a transmission grating. Whenever the light is incident on this grating, whenever the light is incident on this grating, it is opposed, it is blocked by the opaque medium because that is not transparent. So that grating, such type of grating is known as a transmission grating. And now an arrangement which consists of a large number of parallel slits of the same width and separated by equal opaque spaces is known as diffraction grating. How the light will be diffracted through this grating? So that means the grating of light, that is known as a diffraction grating. See, let E be the width of the line and D be the width of the slit. So line width is E and the slit width is D. Now E plus D is known as a grating element, that means our pitch of the grating or grating element. If M is the number of lines per inch on the grating, then so we are considering, see in the previous case, we have the indication 15,000 lines per inch. So here the inches should be converted into either centimeters or meters. Now we are converting the inches into centimeters. So 1 inch equals to 2.54 centimeters. So n into E plus D, so n number of lines into E plus D, that is a grating element, equals to 1 inch, that is 2.54 centimeters. Now we have to know E plus D, that is equal to 1 inch by n, that is 2.54 by n number of slits. How many slits we are using? Here in this case we are using a 15,000 slits. So whatever the slit we are using, we have to add that number n. Due to the above fact, the width of the slit is very narrow and is comparable to the wavelength of light. The slit width is comparable with the wavelength of light. See here, whenever, in every case, whenever we are using a monochromatic source, we can get the bright and dark alternate bands. While using white light, the diffraction will occur in the pattern of rainbow colors. So that's why we are indicating the central, that is a white, central part is white, and remaining is first order rainbow, second order rainbow. There is an intensity difference. So when a light falls on a grating, the light gets diffracted through each slits. As a result, both diffraction and interference of diffracted light gets enhanced and forms a diffraction pattern. So this diffraction pattern is a grating spectrum, that is known as a grating spectrum. Let us see. The condition to form the principal maxima in a grating is given by, so we are obtaining the principal maxima condition here from the grating. What is the condition? Means E plus D sine theta equals to n lambda. Now sine theta by n equals to, so E plus D means 1 by n, 1 inch by n, 2.54. So E plus D equals to 1 by n. So sine theta by n equals to n lambda. Lambda equals to sine theta by n into n. So this equation is known as a grating equation. So from that grating equation, what are the points we gain? What we have to observe means for a particular wavelength lambda, the angle of diffraction theta is incident for a principal maxima of different orders. That is for different orders. And as the number of lines in the grating are large, maxima appear as a sharp, bright parallel lines and are termed as spectral lines. So see here, those are the spectral lines which indicates the Whipsier colors: 0 order, first order, second order, third order. So as the number of lines in a grating are large, so maxima appear as sharp, bright parallel lines and are termed as spectral lines. For white light and for a particular order of n, the light of different wavelength will be diffracted in different directions. So the diffraction is also depends upon the wavelength of each color. Spectra of different orders are situated symmetrically on both sides of 0 order. So in the previous diagram also we saw that already. The spectral lines are more and more dispersed as we go to higher orders. According to the higher orders, the spectral lines are more and more dispersed. And see what is the maximum number of orders possible with a grating. So while we are using a grating, how maximum number of orders we can gain means when light is incident normally on a grating, in the transmitted light on either side of the central maxima, we get higher order diffracted rays. But there is a limit on the maximum number of orders available with a grating. So there is a limit for the grating. Let us know. So sin theta equals to n into lambda n. The maximum value of theta can have is 90 degrees. Whenever the value of theta, that's a maximum at 90 degrees. Hence the maximum possible value of sin theta equals to 1. Maximum possible value of sin theta equals to 1. That means in lambda n is less than or equal to 1. So that is always less than or equal to 1. Hence we are getting n less than or equals to 1 by lambda n condition. So whenever the theta is maximum, the maximum value of theta is also can have 90 degrees. Now the maximum possible value of theta is 1. Whenever the sin theta theta becomes 90, it becomes 1. So the maximum is 1. Okay, and the maximum number of orders possible with the grating, that is depends upon this equation.